Swayam Prabha. Digital India. Educated India.
Welcome to chapter 2, the language of bits. So in this chapter we'll study everything about bits, which is a basic 0 or 1, and what they can achieve. Again, these slides are part of the book Computer Organization Architecture, published by McGraw-Hill in 2015. So here are the 5 main points that we'll cover. Boolean algebra. So Boolean algebra is the algebra of basic bits. How to represent positive integers with zeros and ones. How to represent negative integers with zeros and ones. How to represent numbers with a decimal point called floating point numbers with zeros and ones. And how to represent pieces of text, namely strings, with zeros and ones. So what does the computer understand? The computer is not smart enough to understand languages that we human beings can understand, and that is languages such as English or Arabic or French. Computers are not even smart enough to understand programming languages such as Java and C++. That's the reason it is typically necessary to use a compiler which can convert a Java program or a C++ or a C program into a sequence of basic zeros and ones which the computer can understand. So this process, as we have discussed in chapter 1, is known as compilation, and this is typically done by a compiler. So let's define the terms with regards to zeros and ones. So a bit means a basic variable which can take only 2 values, which is a 0 or a 1. A byte is a sequence of 8 bits, which means 8 numbers where each number can either be 0 or 1. A word is a sequence of 4 bytes or 32 bits. And a kilobyte, so kilo here means 1000, is defined as 1024 bytes. Why 1024 is interesting? So as we shall see, 1024 is an interesting number in the sense that 2 raised to the power 10 is equal to 1024, and this gives us some interesting properties to reason about such systems. So typically, when to use the word kilo, you will find mixed references. In a sense, in some places it is used for 1000, in some cases it's used for 1024. Typically in computer science we would use kilo, the term kilo as in kilobyte, as 1024 bytes, because 1024 is 2 raised to the power 10, and as we shall see in the later half of this chapter, that this gives us some interesting properties. Similarly, we can define mega. So mega is kilo times a kilo, which is roughly 1000 times 1000 or a million. And in computer science, mega is typically 2 raised to the power 10 multiplied by 2 raised to the power 10, which is 2 raised to the power 20. So this is what a million is, a megabyte, and this is close to 1 million 10 to the power 6. So as a result, you will find both the numbers being used, and which variant is being used needs to be inferred from the context. So now let's take a look at some basic logical operations on bits. So a bit is also called a Boolean variable in honor of George Boole. So a bit is also called a Boolean variable. So a Boolean variable can only take values 0 or 1. So let's define some simple operations. So let's first define the OR operation. The OR operation means either, so before that let me define the context. So A can take only two values 0 or 1. So typically 0 is also called false, which means that a statement is not correct, and 1 also means true. So in the context of this we can interpret the OR operation. The OR operation says either A or B, which means that either one of them is true. So let's take a look at what this means in this table over here, which is also called a truth table, because a truth table typically has all combinations of the input values and the final function. So as we can see from here, if A and B both are 0, which basically means if both the values are false, say A or B, so also a mathematical symbol for OR is plus, say A or B is also 0. So in terms of common sense, it can say that look, if two friends, the name of one friend is A and the name of a second friend is B, if both of them are saying something which is false, then we can say that the combination of A and B, both of them together, are also saying something that is false, or nobody is telling the truth. Now, if it is possible that A is saying something that is true and B is saying something that is false, we can say that, the combination of A and B, at least one of them is speaking the truth. And this logic is this OR logic, which means either A is true or B is true, is actually correct. It is true because one of them is 1. So the final output is also 1 over here. Similarly, a symmetric situation holds over here, that if A is 0 and B is 1, at least one of them is 1. So A or B here is also equal to 1. Finally, if A is 1 and B is 1, at least one of them is 1 is correct. So the final output is 1. So this is the OR logic. The OR logic basically says that only if A is equal to 0 and B is equal to 0 is the final output equal to 0. Otherwise, it is equal to 1 in all cases. Similarly, let's define the AND operator on Boolean variables or Boolean bits. And typically the symbol for AND is a dot, as I've shown over here. So let's take a look. So let's again assume two friends A and B. We want only if both of them are speaking the truth, which means 1, do we want to make A and B equal to 1. Otherwise, it is 0 in all cases. So we can see, in a sense, this is similar to multiplication as well. So if A is 0 and B is 0, we say that A and B is 0 because in let's say in the example of speaking the truth, both of them are definitely not speaking the truth. If A is 1 and B is 0, both of them are also not speaking the truth, because in this case B is saying something that is false. So you can see that 1 and 0 is equal to 0. Similarly, a symmetric situation holds over here, where 0 and 1 is equal to 0. So when is an AND function positive? It is positive in only one case, which is the last case that I am showing over here, where A is equal to 1 and B is equal to 1. This is when both are speaking the truth. So let me give an example. Let's assume that you have two friends, right? And for simplicity, their names are A and B. And let's assume that they go and you want to ask A that have you had an ice cream. If A speaks the truth, then you give A 1 point. Otherwise, you give A 0 points. Similarly, we ask the same question to B, and if B speaks the truth, B gets 1 point. Otherwise, B gets 0 points. So in the case of, in this particular case, we have, if you want to have an AND logic, you say that the function A and B, the function A and B is true if both A and B individually are speaking the truth, which means that A is equal to 1 and B is equal to 1, then A and B is equal to 1. Otherwise, in all the other cases, the output is equal to 0, as we can see over here. So we will be using these two basic functions, the OR and the AND function, in detail. So you can take a look at the book for more details, or another book on Boolean logic and Boolean algebra to get a slightly deeper perspective on the OR and AND functions. We can have a similar function, a NAND function. So a NAND function is actually the Boolean inverse. So let's first define this complement operator of an AND. So what is a complement? A complement is very simple. The complement of 0 is equal to 1 is essentially inverts. So if you have a 0, the complement of this is 1 and the complement of 1 is equal to 0. So a NAND function, whenever the AND function yields a 1, NAND yields a 0, and when AND yields a 0, NAND yields a 1. So it is like a inverse of it. So as we can see, take a look at the truth table over here. Let me just show you the previous one. We have 0, 0, 0 and 1. So this is the exact inverse of it, where we have 1, 1, 1 and 0. So this is the exact inverse of the NAND is just a complement or a NOT of the AND function. Similarly, the OR function has an inverse also, which is the NOR function over here, NOR. And if I show you the OR function, if you take a look, you have 0, 1, 1, 1. Here you have a reverse, you have 1 over here, and the remaining 3 entries are zeros. So it turns out that both NAND as well as NOR are universal operations, in the sense that they can be used to implement any Boolean function. We are not at the point where we can prove this result, but this will be an interesting result for students to remember, that NAND and NOR operations, you can implement any kind of logic, any kind of function. So you can take a look at the book, you can try proving yourself, or look at sources on the web or other books for a very detailed proof of this result. Let us now discuss the XOR operation or the exclusive OR operation. So it has a different truth table. So one thing the readers might have realized up till now, that if I have two variables, I can create a lot of different kinds of truth tables. So how many truth tables that I can create? Actually, I can create 16 truth tables. The reason is like this, that every truth table that I have over here will have precisely 4 rows. Right, as you can see over here, it will have precisely 4 rows, row 1, 2, 3 and 4. Each row will have a combination of, a unique combination of the different variables. So it will have 0, 0, 1, 0, 0, 1 and 1, 1. And for each combination, we will store what is the output that this function is supposed to give. So in this case, we have 2 variables. So for 2 variables, we have 4 rows. And for each row, we have a choice that the output can either be 0 or 1. So essentially, we have 2 choices per row. So how many total choices do we have? We have 2 to the power 4 choices, or 16 possible truth tables we can build, or 16 possible functions we can build if you have 2 variables. And the XOR function is one such function. So let's take a look at its properties. So the XOR or XOR, that's how it is called. The X stands for exclusive OR. Exclusive OR basically means that it is true only when one of the variables A is 1 and B is 0, or A is 0 and B is 1. In the rest of the cases, it is equal to false. So as we can see in the first row, both A and B are 0 and 0. So A or B is 0. Similarly, in the last row, both A and B are 1 and 1. So A or B is also 0. But in the middle two rows, the second row and the third row, A is equal to 1 and B is equal to 0. Or alternatively, in the third row, A is 0 and B is 1. So as a result, in these two rows, A or B is equal to 1. And in the rest of the two cases, A or B is equal to 0. So this is one more kind of function as we have seen. So just to make a review, we saw the basic NOT operator. So NOT operator, or so NOT is also called the complement operator. So what this does is that given a Boolean variable, you just place a bar on top of it. So if its value is equal to 0, after a NOT, the combination will become 1, and 1 bar or NOT of 1 will become 0. So one property of the NOT operator is that with a double negation, in a sense a NOT of a NOT will essentially reduce it to the same variable, right? So NOT of A is equal to A itself. Then we saw the OR and AND operators. So the OR and AND operators, the truth table basically for the OR says, if one of the variables is equal to 1, the output is equal to 1. And the truth table for AND says that all the variables need to be 1. So let's take a look at some of their basic properties. So we have the property of identity. The property of identity is like this, that A or 0 is equal to A. This is very easy to verify. If A is equal to 0, then the output here is 0. If A is equal to 1, then the output here is 1. Similarly, we can verify the same property for the AND operator. If A is 0, 0 and 1 is 0. If A is 1, 1 and 1 is 1. So this is called identity, which basically means that any Boolean variable ORed with 0 is equal to the variable itself, and any Boolean variable and 1 is equal to the variable itself. We have a similar property in the same vein called annulment, which basically says that A or 1 is equal to 1. So let's see why. If A is 0, 0 or 1 is 1. If A is 1, 1 or 1 is 1. We can similarly verify the property of annulment for this, that any number ANDed with 0 is 0. So any Boolean number. So in this case, if A is 0, 0 and 0 is 0. Even if A is 1, 1 and 0 is 0. So as we see, so we can use a similar logic to prove properties for all kinds of Boolean formulae. So let's take a look at some more. I'll be discussing some of these properties. I put it on the reader to actually consider a more detailed text. So it can be this book, or it can be other books that are fully devoted to Boolean algebra to take a look at these properties. But they are simple properties, so it's not necessary to consult a lot of text for this. A simple if you just sit down and work it out, it's good enough. So let's take a look at this property called idempotence. It says that any number ORed with itself is the same number. We can easily verify 0 or 0 is 0, 1 or 1 is 1. Similarly, any number ANDed with itself is equal to the number itself. This also can be easily verified. The property of complementarity is interesting, which says that any number ORed with its complement is equal to 1. Easy to verify. Consider 0. Then you OR it. So the NOT of 0 is 1. 0 or 1 is 1. Then you consider 1, and 1 will get 1 complement is 0, so 1 or 0 is also equal to 1. And similarly, we have this property over here, which is A and A bar is equal to 0, can easily be verified in the same fashion. The next property of interest is commutativity. Here A or B is equal to B or A means that the order of variables does not matter. Similarly, A and B is equal to B and A, the order again does not matter. We also have, similar to normal decimal addition and multiplication, we have associativity, which is A or B or C, B or C being here in brackets, is same as A or B or C. So it doesn't matter where you place the brackets, you can place them here and here, or you can place them here and here. For Boolean logic, it does not matter. We have a similar set of rules for the AND operation as well. So for example, here we can place B and C inside a bracket, or we can place A and B inside the bracket, doesn't matter. So you can, readers can manually put in different values of A, B and C and verify, but the results will be as it is. Then we have distributivity. So in distributivity, what this means, it's similar to what we have in regular arithmetic, like x multiplied with y plus z is equal to x multiplied by y plus xz. So this is the law of distributivity that we get to see in regular math. Exactly the same thing holds for Boolean algebra as well. So what we see over here is that A and B or C is exactly the same as A and B or A and C. So this particular formula over here should be verified by the students. A nice way of doing it is just create a simple truth table. Have A, B, C, and then consider the results. Consider the result of A and B or C, and then consider this expression over here. Just bring it here and compute it. So you will see that for each and every row, the values match. Say the values match for all the rows. It means that both the formulae are the same. So exactly a similar formula holds if I interchange and or. Say A or B and C in brackets is equal to A or B and A or C. So many such rules can be used. These are all the basic rules that we have, and with that we can construct complex formulae. So I request the readers to go to the book, read all the rules of handling bits of Boolean algebra. What is Boolean algebra? It's the rules for handling bits and operations with bits. What are the basic operations? Well, it's the NOT operation. As an example, this is A naught. It's the OR operation, something like A or B. When is A or B true? When at least one of A or B is equal to true or equal to 1. Similarly, we have the AND operation. When is A and B equal to true? When both A is true and B is true. So here are two very useful rules. They are called the De Morgan's laws. So some of the students would be familiar with De Morgan's laws. They were there in set theory. So what they say, this is exactly the formula that was there in set theory. It has essentially come to Boolean logic via set theory. So the two so this says that A or B complement is A complement and B complement. So let's verify this. Let's see if this De Morgan's rule is actually correct or not. So let's verify this by. So let's have A or B complement and A complement and B complement. So let's consider all possible values. So 0 and 0, A or B, when both are 0, this is 0, so complement of 0 is equal to 1. So A complement is 1, B complement is 1, so 1 and 1 is equal to 1. So both of them match, which is fantastic. Now let's consider A to be 1 and B to be 0. So A or B is 1 and 1 complement is 0. Similarly here 1 complement is 0. So any number ANDed with 0 is 0. So here also the numbers match. And since this case is exactly symmetric to the case above and the expressions here are symmetric, we can also write 0 and 0. But if you don't trust me, let's work it out. So A is 0, B is 1, A or B is 1, 1 complement is 0. A is 0, 0 complement is 1, and B is 1, the complement of 1 is 0. Any number ANDed with 0 is 0. So we write it over here. Now let's consider the last row. 1, A is 1, B is 1, A or B is 1, 1 complement is 0. Similarly here we have the complement of A is 0. So it doesn't matter what the value of B is, the result is 0. So one thing that we can see is that all our rows match. Since all our rows match, both the formulae are absolutely equivalent. They are the same formulae, they are equivalent. So what we have done is that by the truth table, we have verified this result, which is a very, very important result, that the complement of A or B is equal to A complement and of B complement. We have a similar result where we just replace the OR by the AND and the AND by the OR. So A and B complement is A complement or B complement. So I'll not be proving this. So this is left to a student that you need to prove this with a very similar approach that we have used. Now it's time to take a look at a Boolean relationship which is slightly difficult, and but we can work this out. So this is called the consensus theorem, and this is the statement of the theorem. This is the LHS and this is the RHS, and you'll see many of such burger icons throughout the presentation. So burger means food for thought, so you're supposed to think. So in this case what you're supposed to do is prove that this expression on the left hand side is equal to the expression on the right hand side. So if you want to try, you can always pause the video and think what the solution will be. But let me nevertheless work out the solution. So the first thing that you need to see is you need to take a look at this term. This term is present on the left side and is not present on the right side. So this basically means we need to find a way of eliminating this term from the expression. So how would we do that? The way that we would do that is something like this. Now we expand this term something like this, that any number ANDed with itself is equal to itself. So what we essentially do over here is that we AND it with 1. So let me just expand the LHS side, I'll ignore the RHS side. So basically we still have the same terms. So in this case, the term 1 can be replaced with x or x bar. So we are essentially doing this to ensure that y and z can be eliminated. So what have we done? We have essentially said that any number ANDed with 1 is itself, any number meaning any Boolean number. And now we have replaced the term 1 with x or x bar. After now we can open up the expression slightly and use the distributive rule to open it up. So keeping the rest of the terms, we can have so now what we need to do is we need to rearrange the terms. So let me rearrange them. So let me consider the first and the third term. So since any number ANDed with 1 is itself, so we can write, now let me consider the third term over here. So I'm using the commutative rule to infer that z and x bar is the same as x bar and z. So now we can go up. So any number odd with 1 is 1. So we can replace this with which is exactly what is there in the right hand side or the RHS. So this term is the same as this term, and this term is the same as this term. So essentially we have proven our first complex Boolean relationship or Boolean equation using the simple formulae that we have learned up till now. So mind you, this is a very short presentation of Boolean logic. It is possible to work out much more complex formulae, but for that I would request the readers to consult the textbook, and if they want more information they can look at the book by Z. Kohavi on switching theory. So let's move forward. So we have covered some amount of Boolean algebra. What have we learnt? We have learnt of Boolean variables. So a Boolean variable, let's say b, can take only two values, and so it's a part of the set 0 or 1, and the basic operations that we defined on Boolean variables is not, and or. Then we had some complicated operations like NAND and NOR. We also had the XOR, exclusive OR operation. So these are, maybe these four operations can be considered to be basic. And we looked at some simple rules of manipulating Boolean variables. So now the question arises, why did we learn Boolean algebra? This is something that I didn't tell you, but it clearly has some implication for the rest of the four topics. So let's see. So let me slightly digress at this point, and then we will stitch everything together. So let's take a look at the ancient Roman system of how they were representing numbers. So they had Roman numbers of the form 1 was a single I, 5 was represented with a V type symbol, 10 by X, 50 by L, 100 by C, 500 by D, 1000 by M. So they did not follow a place value system the way that modern numbers are made. So it was very difficult to represent large numbers, and addition and subtraction was fairly difficult in this system. But in an ancient civilization they didn't also have the requirement of representing very large numbers. So this is something that went in their favor. So in comparison, the Indian system, which later on became the Indo-Arabic numeral system, had the number 0, which is the crux of the idea, right? So this is an old script recovered from Bakhshali, which is in modern day Pakistan actually, from the 7th century AD. So it uses the place value system. So what is the place value system? Any number of this form is 5 times 10 to the power 3 plus 3 times 10 square 0 times 10 to the power 1 plus 1 times 10 to the power 0. So the number 10 over here can be considered to be the base. So this particular example is an example in base 10. So why do we use base 10? Well, simple. We have 10 fingers, so that's how we learnt counting in the first place. That we count with our fingers from 1 to 10. What if we go to another planet, a planet which is far, far away, where people have only 2 fingers, right? So the entire planet, all the people there are very intelligent, but they have only 2 fingers. So instead of base 10, they would actually use base 2. So in base 2, how would you represent a number? The way we would do that is if you consider 5, 5 would be represented as 1 times, so 2 square plus 0 times 2 to the power 1 plus 1 multiplied by 2 to the power 0. So in a sense, the number would be 101, which is exactly what we get to see over here. So similarly, what would the number 3 be? The number 3 would be 2 to the power 1 plus 2 to the power 0, which can be represented as 1 in, let's say, base 2. We'll use the subscript for the base. So so this is also called the binary notation, or the base 2 notation. So what we see over here is that it is not necessary to use a base of 10 to represent a number. We can use a different base as well, and we use 10 because we have 10 fingers, but you can use base 2 if you have just 2 fingers. And any numbers, I have shown many examples, can be represented in a base 2 notation. Let me give one more example. Let's say number 19. How would you represent that? So it's very simple. It's 1 times 2 to the power 4, which is 16, plus 0 times 2 to the power 3, plus 0 times 2 square, plus 1 times 2 to the power 1, plus 1 times 2 to the power 0. So this would be equal to 1, 0, 0, 1, 1 in base 2. So this is so 1, 0, 0, 1, 1 is the way that we would represent the number 19 in the base 2 system or the binary system. So now let's define two terms, the MSB, the most significant bit, and the least significant bit. So the leftmost bit of a binary number, for example, of the number 1110, the number shown over here, the most significant bit is 1. And the least significant bit is the rightmost bit, and in this case it is 0. So similarly, we can define numbers in other bases as well. So it is very common in computer science, in computer design, to represent numbers in base 16. So these are called hexadecimal numbers. So what is the problem in representing numbers in base 16? So let's first take a look at base 10. So in base 10, what are our digits? Our digits are 0 till 9. So we have 10 digits. In base 2, how many digits do we have? We have 2 digits, 0 and 1. So in base 16, we need to have 16 digits from 0 to 15. But the problem is that till 9 we have digits defined, but beyond 10, right, we don't have our digits defined. So that's the reason what we do is we use the set from 0 to 9, and then we say that A represents 10 in decimal, of course, B represents 11, and in the same vein, F represents 15. So A, B, C, D, F are the 6 extra digits that we create to represent a number in base 16 or an hexadecimal number, and these 6 extra digits represent the numbers 10 to 15. So the way we represent a number, hex number, is that we typically add 0x before it. For example, 0x9 is actually 9 in base 10. Similarly, 0x 32 is equal to 3 times 16 plus 2 times 1, which is actually equal to 50 in base 10. So I would like to request the reader at this point of time to take as many numbers as he or she wants and convert them to base 16 and convert them to any base of their choice and just see how this works out. So similarly, we can have octal numbers. So an octal number is in base 8, and here we will have 8 digits 0 to 7, so which is fine. We don't need to introduce any new digit, and octal numbers start with a 0, so maybe the number 042 will be equivalent to 4 times 8 plus 2. So this is equal to 34 in base 10. So we can work through many more examples, but I would suggest that we move forward and the reader spend some time at this particular at this slide, which is slide 19, to convert numbers between arbitrary bases. Let us now discuss why we chose the binary, the octal, and the hex formats. Well, the binary is very straightforward. Computers understand the language of only zeros and ones. So as a result, if you have a number system that represents everything in terms of zeros and ones, which is a binary or a base 2 number system, this is information that the computers can process. So what about base 8 and base 16? Well, base 8 and base 16 will turn out to be shortcuts for the binary form, but how that's the case, that is slightly more complicated. So let's work it out. So consider any number, right? Let the number be n. So we can say that the number is of the form so we can sort of break it down into sums of powers of 2, and each of these numbers a0 to ak can be a binary number in 0 and 1, which is exactly our binary representation. So the binary number would essentially be so this is something that we already know. Now we can alternatively say that this is equal to So what we have essentially done is that we have grouped the terms into groups of 3 terms, and the way that we have grouped them is something like this, that we take 3 terms. So the first term is clearly is a0, and 2 to the power 0 is 1. Then we take 2 times a1 and 4 times a2, which is also 2 to the power 1 and 2 to the power 2. Similarly, when we come to the next term, so we again group the terms. So the third term over here is a3 multiplied by 2 to the power 3. So what I have done is that I have brought 2 to the power 3 outside the bracket, and similarly we have something similar, sorry, this is a plus, A3 plus 2 times A4 plus 4 times A5 and so on. So the interesting thing is that if we consider each of these numbers A0, A1, A2, all of these numbers till AK are essentially all of these numbers are either 0 or 1, they are Boolean bits. So if I consider this term, the maximum value of this term is 4 times 1 plus 2 times 1 plus 1, which is 7. And the minimum value for each of these terms, this one or this one or this one, is 0 when all three other coefficients are 0. So alternatively, the way that I can write is that this entire coefficient, I can think of this as B0. So I can write this as so what we have essentially done is that we have expanded this number in terms of powers of 2, then grouped together 3 terms, and then essentially we have expanded the number in powers of 8. So for those who have not been who have not had that magical bulb light inside you up till now, the magical bulb is like this, that we have essentially broken down n into a sum of powers of 8, which is nothing but a number in the octal notation. Say let's assume that the last number in this series is k dash times 8 to the power k dash. So essentially the octal number will be equal to, so this is the number in base 8. So what is the important thing that we learn over here? The important thing that we learn over here is that if we group terms into groups of 3 and each of them is essentially an octal digit, right? So basically if we let's say group them into 4, each of them is a hexadecimal digit. So this gives us a very nice and short form of writing binary numbers in other bases that are a power of 2. For example, if we have this number over here, we can group it into blocks of 3, and each such block we can convert it into an octal digit. So this number, I'm sorry, there's a mistake over here, it should be 7. So this number is a 7, this is a 2, and this is a 6. So this is 0, 6, 2, 7. Similarly, we can take this number over here, and if you want to convert it to base 16, that is also very easy. We group 4 binary digits. So we 1111 is an F, 0010 is 2, and 1110 is well, so 1110 is 12, which is the hex digit C. So what we have is that we have a very compact representation for 12 binary bits using 3 hexadecimal digits. Hexadecimal is abbreviated as hex. So what do we see over here? What we see is that the binary, the octal, and the hex formats are essentially the same. The binary format is very sparse. The other formats are slightly more dense. So this, in a sense, is desirable if you want to represent binary bits. Instead of representing them as ones and zeros, we can, at least while writing or while programming, we can represent them as hexadecimal digits, where we group digits into blocks of 4, and each block is replaced by a hexadecimal digit. Similarly, when we need to expand a number in the hexadecimal notation to a number in the binary notation, all that we need to do is take each of these digits and replace them with 4 binary numbers, and we will have the binary notation.